Hi guys, in this video I'm going to cover what you need to know for your exam with respect to complex numbers. Right? So what is a complex number? Where did it come from? You see, a long time ago, mathematicians were trying to solve this equation here, x squared is equal to minus 1. And the reason that was a problem for them was because you can't think of any real number such that when you square it, you get minus 1. So what they did is they defined the square root of minus 1 as I. And using this, which is called an imaginary number, they realized that they could actually solve any polynomial equation, right? So the complex number, let's call the complex number z, that's the usual notation, actually uses this imaginary term here, right? So the complex number z can be written as a plus bi, where a and b are real numbers, but this is the real part we abbreviated REZ, and this is the imaginary part. So a complex number is made up of a real part and an imaginary part, right? And it is important to note, we could talk about some of the operations we can do on complex numbers, because just like real numbers, we can add them, subtract them, multiply them, and divide them, right? So operations on complex numbers. So let's say we have two complex numbers, z1 and z2. We'll call z1 a plus bi and z2 c plus di. Right. So we define addition like this. z1 plus z2 is a plus c. We add the real parts and we add the imaginary parts, right? We can do subtraction. c1 minus z2. We subtract the real parts and we subtract the imaginary parts, right? We can multiply two complex numbers. Right, so if we had z1 times z2, then it's a plus bi times c plus di, and we could use our distributive law here. So we'll do a times c plus a times di, right? So ac plus a di plus, and now we do bi times c and bi times di. Right? So bi times c is cbi, and then we have bdi squared, right? Think about it like x, because x times x is x squared, I times I is I squared. But remember we said I is the square root of minus 1. So what is I times I, or I squared? Is square root of minus 1 times the square root of minus 1, which is just minus 1. So we could actually simplify this one step further. This is AC plus, and we could group these, AD plus BCI minus, because I squared will become minus 1, BD. Right, so our real part is AC minus BD, and our imaginary part is AD plus BC. Of course, it doesn't really matter where you write the I before or after, right? Nice. And we could, of course, divide two complex numbers, right? So we have z1 divided by c2, which is a plus bi divided by c plus di. And what we do when we're dividing two complex numbers is we do something called rationalize them. And we rationalize, just like when you had surds, by the complex conjugate. So we're going to multiply by c minus di over c minus di, right? This doesn't change the value because c minus di over c minus di is just 1. So it doesn't change the value, but it'll change the form. So now we have a plus bi times c minus di, right? So that's ac minus ADI plus BCI minus BDI squared all over. On this side now we have, oh, and by the way, this is actually a difference of two squares, right? This is C plus DI, C minus DI. So we could just square the first term, C squared, minus and square the second term, DI squared. Right, so let's see what we get when we simplify. We know that this I squared here turns to minus 1, so we're left with the real part is AC plus BD plus, we could do BC minus ADI. That's the numerator, and the denominator is C squared minus D squared I squared. I squared is minus 1, so C squared plus D squared, right? And this here is actually, if we write it like this, AC plus BD over C squared plus D squared plus BC minus AD over C squared plus D squared. Well, you see, this here is going to be a number, a real number, we could call it X, and this here is a real number, we could call it Y. So our answer is actually X plus YI, which is the same as the same complex number 4, right? So this is how you divide two complex numbers. Right, so that and those are your operations on complex numbers. Now we want to talk about the geometric relationship, or maybe I should say geometric representation of complex numbers. Right, so if we want to think of a complex number in terms of points, a point on a diagram, what we could do is we could plot the real part and the imaginary part. So let's draw a diagram that looks like our regular Cartesian plane. Right, so this is kind of the setup for our plane, right? We usually have y up here and x down here, but instead of x, we'll put the real part, and instead of y, we'll put the imaginary part. Then we could write a complex number. So let's say we have z is equal to a plus bi. That is a units this way, and then b units this way. So we actually get something that looks like this. Right? And we went a units on the horizontal axis and b units on the vertical axis. So this is called an Argand diagram. So if you see a question that says represent the complex number on an Argand diagram, all you need to do is put your real axis, imaginary axis. You move a units on the real axis and b units on the imaginary axis. Right, so similar to when we did vectors, this leads to a very interesting notion of length when we talk about a complex number, right? So similar to vectors, if we take the length or the modulus of the complex number, well, using Pythagoras' theorem, it is the square root of a squared plus b squared. And that is the length of this, or the size or the magnitude of this complex number. And of course, this complex number makes an angle with the real axis. So this angle is called the argument of a complex number, argz. And here's something interesting about this, right? The argument in this quadrant here is given as tan inverse of b over a. How did we get that? Well, this side here is opposite. This side here is adjacent. We know tan theta is opposite over adjacent, so theta is tan inverse of opposite b over adjacent a. But here's something interesting. I just defined theta as the angle between the complex number and the real axis. But what I should have said is it's the angle between the complex number and the positive real axis, right? Because if we had a complex number over here, right, so this went maybe minus a units on the real axis and b units on the imaginary axis. Well, when we think of the argument, we are actually measuring this angle here. It's the angle between the complex number and the positive real axis. So how would we find this angle? Well, first things first, this is an entire rotation of 360 degrees, right? A circle, right? Or 2 pi. So this half here, this semicircle here, is a rotation of pi degrees, or pi radians, sorry, right? So this angle here is pi minus the angle over here. What is the angle over here? Well, the angle over there is tan inverse of b over a. Now, why is it b over a and not b over minus a? Because to get this tan inverse figure here, we're thinking of it like this. We want the angle here, and we have opposite and adjacent. So if we do it like this, we are not concerned with the sign. We are only concerned with the magnitude, right? So this is B units and this is A units. We're not really worrying about the direction. We just want to know what the magnitude is, right? So if we have a complex number here, and the second quadrant is actually pi minus tan inverse of B over A, right? And of course, we could extend this idea to the other two quadrants, right? So we have our imaginary axis here, and we have our real axis here. And now we have a complex number in this quadrant over here, right? So we had minus A units this way and now minus B units this way, right? And this is our number here, alpha. But I said that we wanted to measure the argument from the positive real axis. So we want this angle here as theta, right? So theta in this case, well, the semicircle is pi radians. And we have a little bit of an angle over here that we need to add to get this total blue angle. Right, now what is that? That is plus tan inverse of B over A. Now again, why didn't we use minus A or minus B? Because we are only concerned with the magnitude when we do it like this, right? And then if we look at the last quadrant now, right, imaginary here, and real here. And then we have a guy coming here. Now look at this. We want to know what that angle is, right? Because again, we're going to the positive real axis and we are actually going in an anti-clockwise direction, sorry, a clockwise direction, right? So we're going this way, right? We call this little angle there alpha. And we went minus B units this way and we went E units this way, right? Well, the entire rotation is 2 pi or 360 degrees. And we're just cutting out that little part there, which is tan inverse of B over A. So the last thing we'll talk about in this little introduction is that we know we have a complex number z is equal to A plus IB. We know that we could represent that complex number on what you call an Argand diagram, right? Just putting in the solid lines for now. This is our imaginary, this is our real, right? Of course, this is a perpendicular here, and this is the angle theta. We move A units along the real axis and B units along the imaginary axis. We know that this is the modulus or length of the complex number, this hypotenuse here. But what if we were to employ a little bit of a little bit of trigonometry? This is the opposite angle to the angle. This is the adjacent, and this is the hypotenuse, right? So we know that cos theta, which is adjacent over hypotenuse, can now be written as A over mod z. So what is A? The side A is mod z times cos theta, right? And similarly, we could find B is mod z times sine theta, right? So let's give this mod z a different name now. Let's call this mod z R. We're calling it R. R. So we have A is R cos theta and B is R sine theta. Then this complex number z is equal to A plus IB, we can now write as z is equal to A, which is R cos theta, plus B, which is R sine theta I, right? So if we factor out the R, we get z is equal to R cos theta plus I sine theta. And this is called the polar form of a complex number. Right? This is the polar form of the complex number. And this is the rectangular or Cartesian form of the complex number. Right? And we can actually go one step further from the polar form and we can say, okay, let's write this complex number as R e to the I theta. And what is this? This is the exponential form of a complex number. Right? So in the next part of this video, we'll look at why the polar form is so useful. So now that we have the polar form of the complex number, we can look at a very useful theorem related to it called the Morse theorem, right? Which states if we have a complex number R cos theta plus I sine theta, right? This is the same polar form we found earlier, polar form. Right? And we raise the complex number to the power n, where n is any rational number, then the result is n to the n into cos n theta plus I sine n theta. Right? This is De Morse theorem. And De Morse theorem, and let me just make a note, this is any rational number here. De Morse theorem actually has some very interesting applications, right? For one application, we could solve equations. So let's look at an example here. Let's say we have z cubed is equal to 1 plus I. And we want to solve for z. Or we want to find the roots of this equation. And the roots are, of course, the values of z, which make this equation true. Now, let's just look at this here. Z cubed, right? So we're expecting 3 roots, just like with polynomial equations. So to solve this using the Moivre's theorem, first we want to write the right-hand side in polar form. Right. How do we go from rectangular form to polar form? Well, we have that a plus ib becomes r into cos theta plus I sine theta. So we need r and we need theta. R is the length or the modulus of the complex number, which is given by the square root of a squared plus b squared, which is root 2. The argument is tan inverse of b over a, which is pi on 4. You can check that on your calculator. Why is it tan inverse? Because if we look at a quick Argand diagram here, we have our real side, our real axis, on our imaginary axis. And this goes 1 unit on the real and 1 unit on the imaginary, right? This is 1 plus 1i. You can think of it like that. Right. So we have our r, we have our theta. So we could write z cubed is hence equal to, instead of 1 plus I, we put root 2 cos pi on 4 plus I sine pi on 4. Nice. Now, something I did not mention previously, but we want to look at now, what would happen if I make a complete revolution of 2 pi and end back up right here on this complex number? Well, we'll get the same value. Now, what if I made a second revolution all the way around and I end right back up where we started? We get the same value. In fact, if we add any integer multiple of 2 pi to our argument, we get the same exact value. What that means is if we had the argument as pi on 4, then we'll get the same value if we did the argument of pi on 4 plus 2 pi, or pi on 4 plus 2 times 2 pi, or pi on 4 plus 3 times 2 pi, or pi on 4 times k plus k times 2 pi, or 2k pi. So this is called the principal argument. And we could write the argument of z, so let's just write root 2 cos pi on 4 as a principal argument by adding 2k pi, right? Plus I sine pi on 4. And regardless of the value of k, we should get a consistent number, right? Okay. So just like when we have regular polynomial equations, let's say we had x cubed is equal to 1. Then x is equal to the cube root of 1. So if we have z cubed is equal to this, z is equal to the cube root of this entire thing here, plus pi on 4 plus 2k pi plus I sine pi on 4 plus 2k pi, right, to the power of 1/3 cube root. Nice. So now we can use the Moivre's theorem, right? Because we have r cos theta plus I sine theta to the power n. Right, so we get r to the power n, so root 2 to the power 1/3, which is 2 to the half times 2 to the 1/3, 2 to the half to the 1/3, which is just 2 to the 1/6 cos, and maybe we can simplify this. That'll be, if we bring down n theta, that's 1/3 times, we could factor out pi, and we could factor out 4. We get 1 plus, that should be 8k. Yeah, that's about right. Um, plus I sine n theta, so 1/3. And of course, I just simplified it, right? This is the same theta here. 1 plus 8k. Nice. Right. Right. So the last step here, when they ask about the step, oh no. Oh yeah, we could put step 2 over here, use demos. Theorem. Let's put that one. Right. And step 3 now, find distinct roots or solutions, right? Distinct roots. So how do we do that? Well, there's a distinct root corresponding to different values of key. So let me show you what that means. When k is 0, what do we have? We have z, we call that 1, equal to 2^1/6 cos, and k is 0, so we get 1/3 times pi on 4, which is pi on 12, plus I sine pi on 12. Nice. When k equal 1, we have z2 equal to 2^1/6 cos. What does the angle become? Is 1 plus 8 times 1, which is 9. So 1/3 times 9 pi on 4, which is 9 pi on 12, which is 3 pi on 4. But you can leave it like that for now. 9 pi on 12. And lastly, when k equal 2, the third root is 2^1/6 cos 8 times 2 is 16 plus 1 is 17. 17 pi on 12 plus I sine 17 pi on 12. Right? And if you use your calculator, you will see that each of these roots, these values of z, satisfies the original equation, z cubed is equal to 1 plus I. So that's how you use the Moivre's theorem to solve. So the next application for the Moivre's theorem is used to express sine n theta and cos n theta in terms of sine and cos. Let me show you what that means. For example, we want to write cos 3 theta in terms of sine and cos, right? So let's try this. We know that cos 3 theta plus I sine 3 theta is equal to cos theta plus I sine theta to the power 3. Right? So we kind of just use the Moivre's theorem and reverse that. And let's now expand this bracket here on the right-hand side using the binomial theorem. Right? So we do the first term's cube plus 3 times cos squared theta sine theta plus 3. Oh, this should be I sine theta plus I sine theta, right, plus 3 cos theta I sine theta squared plus should be I sine theta cubed, right? So let's expand this now. We have cos cube theta plus 3i cos squared theta sine theta plus 3, and I squared, we know is minus 1 cos theta sine squared theta plus I squared is minus 1, and we have an I left because this is I cubed, so I squared times I, which is minus 1 times I sine theta. Right, so if we group this now, we have cos cube theta plus, oh sorry, minus 3 cos theta sine squared theta, right, plus I into 3 cos squared theta sine theta, minus sine theta. Or this should be sine cube theta. Yeah. Right? Then sine cube theta, sine to the power 3. Nice. And what we have here is a real number. So this part here, yeah, this here is real. This with the I is the imaginary part. And we see we could actually equate the real and imaginary parts, right? So we just say equating real and imaginary parts plus 3 theta, which was the real part, is cos cube theta minus 3 cos theta sine squared theta. And sine 3 theta, we had I sine 3 theta. So I sine 3 theta is 3 cos squared theta sine theta minus sine cubed theta. Right? So we've just written cos 3 theta and sine 3 theta in terms of cos and sine. So that is another application of the Moivre theorem. The last application now for the Moivre theorem is, let's just call that proof of identities. It's very similar to the second one, but we use a different method to show the identities, right? So let's say, for example, we wanted to prove. Okay, so for example, let's prove that 4 sine cubed theta is equal to 3 sine theta minus sine 3 theta. Right? So unlike the previous example, where we used the moves and brought the power of the index in, what we're going to do this time is look at two sort of sub-identities, right? So first of all, we know z is cos theta plus I sine theta. So using the modes, we could find z to the minus 1, which is just cos theta plus I sine theta to the minus 1. And using the modes, we get cos minus theta plus I sine minus theta, right? And we know that cos of minus theta is equal to cos of theta, and sine of minus theta is equal to minus sine of theta. right? So Z inverse, we could really just see is cos theta minus I sine theta, right? So where do we go from here? Well, first, if we take Z to the n now, using the moles, we have cos n theta plus I sine n theta, and Z to the minus n will give us cos n theta minus I sine n theta, right? So if we add these two, z to the n plus z to the minus n, we get cos n theta plus I sine n theta plus cos n theta minus I sine n theta. Right, so the I sine n thetas will cancel off and we get 2 cos n theta. Or alternatively, we could write cos n theta as z to the n plus z to the minus n all over 2. And you can already see where we're going with this, because we will eventually get terms of cos n theta and sin n theta, right? So this was if we added it. Now let's subtract and see what identity we get. Z to the n minus z to the minus n. Get here cos n theta plus I sine n theta minus cos n theta minus I sine n theta. So now this time the cos's will minus out, right? And the minus on over here will change this to plus, and we'll get 2I sine n theta, right? So we could write now sine n theta as z to the n minus z to the minus n all over 2I. Right? So we're going to use these two identities to help us out here with this question. Right. So for this example, what we want to note is the highest power of sine is sine cubed. So what we might want to do is take sine cubed theta, which is of course sine theta to the power 3. Now what could we do with sine theta? We could write sine theta using these identities. So instead of Zn, we have z to the minus 1. So z to the 1 and z to the minus 1. All right, so the identity will give z minus z to the minus 1 all over 2I raised to the power 3. Now this thing here in the bracket just came from the sine n theta equal this, but using n is equal to 1, right? Right, so let's expand this. So first, we could take out the fraction. Then we'll have z minus z inverse to the power 3, right? So from here, we have 1 over 2 cubed times I cubed. Of course, this is 1 cubed, which is just 1. And we could use the binomial expansion to expand this. So we have z to the power 3, and we need to alternate signs, minus 3 z squared z to the minus 1 plus 3z z to the minus 2 minus z to the minus 3. From here, 2 cubed is 8. I cubed is minus 1, because that's I squared I. Right? And we can start grouping over here. z cubed minus 3. And z squared divided by z is just z plus 3z divided by z squared is c to the minus 1 minus c to the minus 3. Right? We have minus 1 over 8I times, and now let's group the powers that are similar. So z cubed minus z to the minus 3 plus, or maybe we should do minus 3 z minus c inverse. Right, so that takes care of all the terms. And now if we go back up to our formula here, we see that z cubed minus z to the minus 3 is actually just 2I sine 3 theta. So let's put that in here. We have minus 1 over 8I. And this term here, this becomes 2I times sine 3 theta minus 3. And this term here becomes 2I sine theta. 2I sine theta. Right? And now we can divide throughout by I, so we are left with minus 1 over 8 the 2I. Oh, sorry. We could actually divide throughout by 2I. And then we'll be left with 4 for him. So left with minus 1 over 4 into sine 3 theta minus 3 sine theta. Right? And this was initially equal to sine cube theta all the way up from here. So we just carry over the 4 now. We get 4 sine cubed theta, and we multiply throughout by the minus sign equal 3 sine theta minus sine 3 theta, which is exactly what we needed to prove in the original question. Okay, so that's how you do this last application here of the Moivre step. Okay, so the last thing I want to talk about today is the locus of a complex number. So when we say the locus of a complex number, we're talking about the set of all the points that trace out the path of the complex number. So let's say we had z is equal to cos theta plus I sine theta. We know that the modulus of z is 1, right? And this is just because it is cos squared theta plus sine squared theta, a squared plus b squared, which is, of course, the square root of 1, which is 1, right? So if we were to put this on an Argand diagram, we have our real side here and our imaginary side here. This complex number has a length of 1. So if we look at the center over here, could we trace out a path of all the points that have a length of, oh my god, that is very bent. Could we trace out a path of all the points that have a length of 1? And the answer is yes. And the result that we get looks like, oops, looks like this. Right, so the locus of this complex number is a circle with radius 1 and center 0, 0. So let's look at a more concrete example to get the idea of this. Okay, so in this example, we want to find the locus of the complex number z such that the absolute value of z minus 3 is equal to 2 times the absolute value of z plus 5i. So to deal with a question like this, first, we need to define z. So step 1, define z, right? And z is a complex number, so we could just define it by x plus I, y, right? Step 2, we now want to write the equation in terms of x and y, right? So we see here on the left-hand side, we have the absolute value of z minus 3, which is the absolute value of what is z? It is x plus iy minus 3, which is the absolute value of, we could group the real parts, x minus 3 plus iy. On the right-hand side, we have 2 times z plus 5i. Yeah, so we just do the same exact thing. We substitute and we write x plus iy plus 5i equal to 2 times, and we can group it again, x plus y plus 5i. Right. So these two things are equal. So we have the absolute value of x minus 3 plus iy, which is a complex number, real and imaginary parts, equal 2 times x plus y plus 5. Right? It's a good practice to write it consistent. So maybe the I should come in front. Right. So what is the modulus of a complex number? The modulus of z, which is the modulus of x plus iy, is equal to the square root of x squared plus y squared. So if we use that over here, on the left-hand side, we get the square root of the x minus 3 squared plus y squared is equal to 2 times the square roots of x squared plus y plus 5 squared. So we could square both sides, we'll get x minus 3 squared plus y squared equal 4 into x squared plus y squared plus 10y plus 25. And we expand the brackets one time. So this will give us x squared minus 6x plus 9 plus y squared is equal to 4x squared plus 4y squared plus 40y plus 100. And we can bring over everything over to one side, so 0 over here. We get 3x squared. I brought it on this side so it'll stay positive. Plus 3y squared plus 6x plus 40y plus 91 is equal to 0. Alright, so if I divide throughout by 3, I get x squared plus y squared plus 2x plus 40 over 3y plus 91 over 3 is equal to 0. And if we want to describe this locus, we could actually complete the square here. Right, so to do that, we'll take x plus 1 squared, and when we expand this, we get x squared plus 2x plus 1. So we have an extra 1 that we don't need, so we just minus 1 plus, and do the same thing with the y, plus 20 over 3 squared. And when we expand this, we'll get y squared plus 40 over 3y plus, I think it's 400 over 3, or 20 over, 400 over 9. So 20 over 3 squared. So we minus now 20 over 3 squared. Right? Plus 91 over 3 equals 0. So we bring everything over, x plus 1 squared plus y plus 20 over 3 squared. Right, which will give us minus 136 over 9 equals 0. Right, so if we write it in this form, x plus 1 squared plus y plus 20 over 3 squared is equal to 136 over 9, then this is the equation of a circle. So the locus is a circle with center minus 1 minus 20 on 3 and radius square root of 136 over 9 as the locus of the circle. Right, and of course, if you were to draw this on an arc diagram, then we have our real side here, our imaginary side here. Our center is minus 1, so we go minus 1 this way and minus 20 over 3, so maybe here. This is our center, and our radius is that amount. And maybe we do something like that. Well, hopefully drawn a little bit better for school. Right? But that is the locus of our complex number C. So if you are asked to sketch the locus, this is what you need to do on an arc diagram, hopefully a little bit better than my drawing. If you are asked to describe the locus, this is what you do. And of course, if you are asked to find the equation connecting x and y for the locus, this is what you do over here. Right? And that is how you deal with the locus of a complex number. Right? So that should go over everything you need to know for your exam, the basics with complex numbers, solving equations using their moivres, and the locus of a complex number. Right? Okay, bye.